actually, so Herb can, I'll,
Okay.
I'll start, but you might want to cut me off if I get to going too much, so.
Well,
So
okay.
it's Dr. Herb Kraus, correct? That's how you say your name, sir?
Yeah, right.
Okay. And then Dr. Robert Compton, I'm sorry. I don't know why I kept wanting to say Compton, and Mr. Fred Peretz.
Yep, Fred Peretz. Don't need a mister.
Just Fred Peretz, okay. All right, so we are going to open up the evening for the students to trickle in. They're typically pretty quiet as they come in, and they'll just answer the questions. And then, like I said, around 7:05, we will start the meeting. I'll do a little bit of introductory slides, and then I will allow as much time as possible for you guys to go ahead and open up the floor. Any questions? All
Nope,
good?
we'll learn as we go.
Yes.
Okay, I'm gonna start letting the kids in.
Okay. And feel free to answer the trivia questions if you'd like.
Where are these students from? What schools?
All throughout Tennessee,
Oh, okay.
middle school and high school. Okay, so I hope everyone enjoyed a little trivia poll this week. So now we're going to go into our meeting today. We are going to have our meeting around Dr. Robert Compton, Dr. Herb Kraus, and Mr. Fred Peretz today. They are our friends from ORNL. They have greatly supported Virtual Science Club for through our incentives programs and overall in SASAF. So we really appreciate them coming today. So later on, after our introductory slides regarding SASAF, they're going to go around the panel and discuss their various backgrounds and interesting facts about their experience in STEM. We would love if you could hold on to your questions, both in the chat as well as virtually, just waiting until they are done speaking, and then we will open up the floor for questions and answers. All right, without further ado, we'll just continue. Today is December 13th, 2022. So welcome back to Virtual Science Club. Today, per usual, our meetings usually start around 7 p.m. We have 2 meetings per month, one with breakout sessions with our mentors, and then the other session is with guest speakers. Our grades are open to 6 through 12 students, STEM teachers, and leaders. And of course, it is free to attend. Now, this meeting is the last meeting of 2022. So after this meeting, we will be on a break until after Christmas and New Year. So we will see you again the following year in January 10th. So if you would like to go ahead and register for that meeting, go ahead. There's a QR code to do so. The January 10th meeting will be the last meeting, I believe, with the mentors specifically. Now we will have a open office hours session later on in February. So if you do have any last minute questions you want to ask the mentors, you can definitely do so. But that January 10th meeting is going to be specifically for them. And then we're going to have 2 more guest speakers after that, and then Virtual Science Club will close. But do not worry, we have 4 other great programs starting in spring, in which we hope to see you guys soon again. All right. Again, registration for SASAF is open. So for pre-approval deadline, that is coming up on January 18th. Overall registration has to be completed by February 28th, and then SASAF actually starts on the 28th of March. The 30th is going to be the award ceremony, and then that will conclude SASAF. Of course, if you are interested in, my internet connection is unstable. I think, can you guys still see me okay? Okay, all right. So the SASAF registration website is open. And so you can check those QR codes to go into details and see when the deadlines are open and closed. Again, we are covering these counties with SASAF, but of course, if you are not in the immediate location, please let us know. We can try to get you into a different science fair so you can participate. Now, I would like to open up the floor for our friends of ORNL. I believe everyone has access. So Dr. Compton, do you mind starting? Oh, sorry, it was going to be Dr. Herb.
Okay. I'll share a well, I thought that I would talk to you about what I've spent a lot of time doing. So I'm a retired atomic and molecular physicist from Oak Ridge National Laboratory. Just from background, I will tell you that when I started out in college, I thought I wanted to be an electrical engineer. I changed into physics halfway through, And then I went to graduate school in physics and to receive the doctorate degree. And then I came to Oak Ridge and I worked there for 38 years. So I've been doing atomic physics for a long time. So I thought what I would do is introduce you, since we want to talk about some science here. I can also give some advice for VSC students how to excel in science, but we won't probably have time to do that. So what I want to talk about is what atomic physicists do. That's probably something that students haven't heard in their classroom. But in order to do that, I have to, first of all, remind you what an atom is. So if you look at the upper right, you'll see that this is an artist's view of what an atom looks like. In the very center, there's
Herb, let me interrupt you. I'm not seeing your screen. I'm seeing Trixie's.
really.
Is anybody else having that issue?
Yes,
I'm having it also.
if you click the upper left-hand corner, it let me switch who I was seeing screen share.
Okay, well,
So you can do new share and then press on the screen that you want to,
okay.
'cause I allowed it for multiple participants to share simultaneously, so.
Thank you, Bethany. That worked for me.
I still don't see anything.
So
There is a button at the bottom, middle bottom, that says share screen in green.
it says that I am sharing right now.
Yes, now we see
Okay,
it.
okay, now it's going.
Okay, fine.
All right.
Sorry. Okay,
Now I'm
so,
with you.
All good.
so in order to start this, we have to remind everybody what an atom is. And if you look at the upper right-hand corner here, you have in the nucleus, the center of the atom, you have 6, for a carbon atom, you have 6 positive charges. They are protons. Then you have 6 red neutrons for the most common isotope of carbon. And then you have 6 electrons in green that are orbiting around. So an atom is really like a mini solar system where the nucleus takes the place of the sun, and the electrons take the place of the planets. So what atomic physicists really do, they study the atom's interactions with the outside world, among themselves, how the electrons interact with each other, how they interact with the nucleus. So that all is part of internal structure. And then electron dynamics, when you do something to it, when you tickle it. The first thing I want to make a note of is that atomic physicists do not design atomic bombs. They are actually nuclear devices, nuclear weapons, and only engineers with nuclear physics knowledge do that. So that's not what atomic physicist does. So what we really do is that we study the change in in ions, and also the targets and the electrons surrounding each nucleus after a neutral atom collides with a fast-moving ion, or by impact with a beam of laser light when you shine some light on the atom. So now go to the lower right-hand corner, and now this is a conception of actually a cartoon of what of an ion atom collision, where we start with a proton, one of those blue plus charges, hits an atom like carbon, and if the proton approaches fairly slowly, you can get a neutral hydrogen. An electron can hop onto the proton, and just like billiard balls, the angle of both the projectile and the target go off in different angles. So in this case, because the hydrogen, well, the proton picks up an electron and becomes neutral, then the charge on the carbon increases. In other words, the electron hopped off of the carbon and went on to the proton. So that's a collision, and that's one way. A collision is one way of determining what is going on inside of an atom. After all, an atom is really 1/1,000,000th of an inch in diameter. You can't see it. Well, you can sort of see the electron cloud if you magnify it by 10 million times using an electron microscope. But you can't really get inside the atom. You can only see sort of an electron cloud with a microscope. In order to look inside an atom, you have to collide it with something, or you have to tickle it with a laser beam, and that'll cause the electrons to be excited. And if you choose the right color of the light, you can make the electrons pop off, and that's a way of, or you can see it emit light when you shine light on it. So that's one way of learning about what's in the atom. Now, in order to do these experiments, first of all, you have to be able to make a projectile like protons. You make a beam of them. It's like a beam of light, only it's protons. And then you collide it with atoms that are either in a gas, they're sitting on a surface of a solid, or inside a solid material. To do the latter, you have to have the proton going very fast so it can pass through the material. So what atomic physicists really do, in a nutshell, is they measure the direction of these products on the lower right here after they've collided. They measure the speed they come off with, and also the charge that they have. And then sometimes there is light that's given off. Now this ion atom collision is a very slow one. If you come in very fast, it's a more violent collision, and so more things can happen. For example, you can excite the carbon plus ion. You can excite these electrons, and if you hit it hard enough, you can make then electrons be spit off from it. And so it will upcharge to a higher charge state. So all these things, if you study collisions at a whole lot of energies, at a whole lot of velocities, then and see what happens, then you can come up with an idea of really what's going on. And this technique of probing an atom is sort of like learning what's inside of two colliding cars by picking up all the pieces after a collision, and then you sit down, you look at the results, and you solve a puzzle. And the puzzle that you have solved then is something that you will prepare and you will publish. And in that publication, in a scientific journal, you will try to compare to predictions that theoretical atomic physicists have made, if it turns out that they exist, because you want to find out whose theory is the best one that explains the results of whatever you did. It turns out in practice, it's usually the case that there is not a theory at the time that will explain what you saw. But as an experimentalist, as I am, you sit down and you try to come up with some ideas, knowing a lot about the very details that we do know about the atom, try to explain why it happened. That when a projectile went in and electron hopped off, where did it hop off, at what distance it hopped off on, and so on. which is related to the angle that you have measured. And so you can get a lot of information. So why do you want to do this to begin with? Well, it turns out that that by doing enough of these experiments with different projectiles and with different atoms that are relevant in different environments, you can help other scientists learn something that that they would like to know. For example, atomic physics occurs in astrophysics. That is in the atmosphere of stars, in the distant atmospheres of stars. It happens. It also occurs in the upper atmosphere of the Earth. You know, the Earth is surrounded by what is called the ionosphere. It's a lot of ions and electrons that circulate. The ionosphere is a very important region for the Earth because it's responsible for being able to pass through certain wavelengths of light, and also it allows radio signals to bounce off of the ionosphere at lower frequencies, and it helps with communications on Earth. So it's important to understand in the upper atmosphere the physics that's going on there, so that you can predict what might happen. For example, if there's a solar flare. When I say solar flare, I will tell you that the sun periodically emits a lot of protons, and those protons are moving not that fast. They're really about one 100th of the speed of light, which is not that fast. But they interact with our atmosphere, our upper atmosphere, and that's why when there is a solar flare, we can lose our communication ability because of the interaction in the upper atmosphere and the ionosphere. So we want to understand these collisions and and if we can do anything about them. It's also, this kind of research also impacts on electrical discharges. You know, if you were to take a tube and put electrodes in it and put electricity through it, it would glow if it were in a glass, and you'd see that. But there is interesting physics in there, and there's also a lot of good physics in plasma devices. These are devices such as thermonuclear plasmas that may ultimately provide some energy for us. Now, I want to make a real distinction here that there are academic atomic physicists like me, and there are applied physicists and engineers. So now the applied physicists actually develop practical applications using the results that are in the journal. And they sometimes do some similar experiments themselves. So that is basically what they do. Now, I didn't tell you how you do that, but I have some pictures here just to show you. On the left part of the screen, I show you a low energy atomic physics lab, and this is an example where a beam came down, was made, and it came down this pipe, and it went into a chamber here that held a solid crystal, and the idea was to bring the ion beam into a grazing incidence on the crystal, and then let it just slightly deflect. And when an ion interacts with the crystal, electrons jump onto it, and we would like to know. We would like to have a theory that predicts how many electrons will come in and at what angle when you bring it into the surface. So this apparatus was constructed to do that, and it was for ions that were traveling about 1/100th of the speed of light, which is rather slow. Now, you can see here that there's a lot to this apparatus because you have to evacuate the tube. You have to get rid of the air if you want to see these effects. So you have expensive vacuum pumps that get it down to a gas density that's like outer space, and it's ultra high vacuum. And then in addition to that, you have fancy detectors that you don't see here, but to measure the angle and what charge is coming off when the ion comes in and bounces off the surface. So that takes fancy detectors. It takes a lot of fancy electronics, and here's a Macintosh here, a couple of them. And that was used to do some good science. Now I want to contrast that. This kind of science on the left is science that you can do with 1 or 2 or 3 people. I want to contrast that with what happens at a high energy physics lab doing atomic physics. And this is work that I did at CERN near Geneva, Switzerland. First of all, I will tell you that what there are on the border of France and Switzerland, there is this lab, and so what it's actually a huge lab that's funded by all the NATO countries and some others. So in here, what happens is they make ions right here near the center. They're accelerated. They go into a super proton synchrotron, and they're revved up to really high speeds that are close to the speed of light. And then what they actually do then is, after they're sped up, they go into another ring, and this is the heavy ion collider that you hear so much about these days. This is a huge thing. It's 5 miles in diameter. And so the ions that are sped up here start off in France. They come into Switzerland, and then they go around here, and here's the Swiss border again, and they go back into France. So they circulate around the border. They don't need a passport. So once the experiments that I did there, I just used this smaller ring. And after they were sped up, they were spit out here, and we did some experiments. And this is the tunnel. All this is underground because of radiation that would be produced. And here is the tunnel for leaving this SPS ring. And so the beam comes down here. You see, it's really big, expensive science. And then after that, there's a beam. We catch the beam through an apparatus here, and this had targets in it. There was a target wheel, and on the wheel there were about 20 different little samples of different materials, because we wanted to find out what these relativistic ions would do in that target. What you don't see is a fancy detector down here. There was a detector that would measure electron and positron pairs. That is, a positive electron and a negative electron can be produced at these extremely high velocities, close to the speed of light. And we were trying to determine the angle and separate the events that where the positron and the electron came off were formed exactly at the same time. Well, that 100 detectors requires a lot of fancy electronics, and this shows about a third of it that was used. There are just hundreds of cables that were needed to connect these detectors to all this fancy electronics, and we had fancy computers too, but they were Macintoshes also. And so what I want to leave you with is the fact that, first of all, in order to do experiments like this, you can't do it with 1 or 2 people, because there are experts to make the ions. There are experts to put it in this ring. and a whole staff that does that. And all we did was make an international collaboration with other scientists in Europe so that we were allowed to run there and some get help. But this guy right here and me were the principal guys who designed the experiments, analyzed them. This guy did the mechanical work, and I did all the electronics and computer stuff. So, but we had other people to help us set this up. But this is big science that means you must collaborate. The days of not collaborating in science are pretty much over. To do really great science, you need to work with a lot of people. You also, I have to tell you that it's very expensive to do this science. For example, the amount of electronics here alone was more than $500,000. And so you have to raise money to do that and then put it all together and make it work. So, but the nice thing about it is physics done this way allows scientists to travel around the world, go to different accelerators that are good at doing certain things. And that's really, so I'll stop there and I probably took too much time, but ask for any questions. Let me see what's in the chat. Well, I don't see any chat questions. Oh yeah, here we go. Well, I don't, okay.
Yeah, we might be interested in knowing how questions work. Do students get on verbally and ask questions?
It really depends on how you want to do it, but I believe we wanted to wait until all three of you were done, and then we can then do our questions collectively. So the students have the option to unmute themselves and then ask a question, or they'll type it in the chat.
Okay. Well, I'll stop the share then and let Bob take over.
Now the real challenge is for me to get on share screen here. And I want to click share screen. And now I've got to do something here. I've got to go to document, not WordPerfect. What do I want? I want whiteboard, no screen. I'm not sure how to pull up my where am I going here? Can anybody help me? I need to get out of.
Go into share screen.
See what happens there. Well,
there you are. We see it.
Now, all right, I've got that. I've got somewhere, anywhere. Let's see now. I've done this before, but I'm not having.
We're seeing these are galaxies full of billions of stars. Is what we're seeing.
I see that too, but I need to get on my let's see, my I don't know, I'll try this. No, that didn't work. I need to get on my, hold up. I'm really getting screwed up here now.
Well, we see a list of recent documents.
Yeah, that's WordPerfect. I need to get my PowerPoint. Let me get out of that. Well, I've done this millions of times, but it's not working now. Let's see. Let me go to File. Oh boy.
Are you in, Bob? Are you in Word?
No, I'm not, I don't have my thing in Word. It's in PowerPoint.
Can you look for Microsoft Word, the Explorer, the folder, that yellow folder at the bottom?
So
That one?
close out of the Word document. And do you have it on your desktop?
I have it on my, here, desktop. I just clicked on, I have it on desktop. Okay, I'll find it now. Here we go, virtual science talk. Thank you very much. Somebody, whoever that was, we got it.
We're still seeing Word on the screen.
Oh, not really? Okay, mine,
Yeah, just a large black space over your word. Why don't you minimize the word?
now I've got it on mine. I can see it now.
Well,
But you're not seeing it though.
We're not.
You are sharing the wrong file.
Well,
You may want to stop sharing and then reshare.
Yes, and then choose the file you want to share. So stop sharing and then choose the file you want to share.
When that box pops up, hit save.
okay,
Because it's not gonna.
don't save, right? This is embarrassing.
It's
Oh,
fine.
I just went back to share. Okay, what am I doing?
Okay.
Now go down to the bottom and where it says share screen and share again.
All right, now I've got, I can get share screen, PowerPoint, voila. Does that work?
Yeah, okay.
Works for
Yes.
me.
Much better.
Yes.
Okay. Go to slideshow and start at the first
All
slide.
right, thanks, guys. I learned something. No, I'm not sure I learned anything actually, but well, thank you very much. And I actually did some work with on Herb Krause, Dr. Krause's machine out there at Oak Ridge National Lab. I was there at Oak Ridge National Lab for 32 years. And then I spent 20 years doing physics and chemistry research and professorship at the University of Tennessee. And so when I worked there, I did mostly my work in molecular physics, although some was with atomic physics, particularly with machines that Fred was talking about there, Herb was talking about. And the last semester I was at UT, I taught astrophysics or cosmology actually. And I spent all my life doing atomic and molecular physics, but since I've retired, I've found that more interesting than what I did. So we'll talk about that. But during my retirement pages, I've published a couple of books. There's one book that came out just recently. And then I have a book here on lasers that I also published a couple of years ago with a person at the University of Georgia. And so I've done a lot of my work was with lasers, a lot of my work with spectroscopy, various types of spectroscopy, infrared and Raman spectroscopy, all of which is very important stuff. But I want to talk to you about the universe and where we are. And this is what occupies a lot of my free time reading and everything. So I thought I would do that. And you can ask me any questions about anything else that you want to talk about. If you look out at the universe tonight,
Bob, if you would go into if you go into slideshow and then start.
Is that not working?
We're seeing, yeah.
You see it? There's the universe.
Yeah, okay.
The stars, okay? I like to keep this over here to the left side also. So
Okay.
yeah, I like to know where I'm going to. So if you look out at the stars at night, you see just billions and billions of stars in all directions. There's more of a density of these stars in one direction, and that's what we call the Milky Way, which we're part of that galaxy. So a galaxy of stars. And how much of this you can see depends on the kind of telescopes that you have. And you can have a binoculars that will allow you to see the moon better and maybe even see the moons of Jupiter. And if you've ever done that, it's kind of cool. And now what we've done over the period of the last 20 or 30 years, we built better and better telescopes. And the one that came up next was Hubble telescope. And this, now you can see these are galaxies. So if you go back here, if you take one dark spot in here, someplace where you don't see any stars, and you look at that through the Hubble telescope, you see again a much denser density of objects here, and each of these are galaxies, and these galaxies are full of billions of stars. So that sort of puts you in the framework of, boy, there's a lot of stuff out there, and we're pretty small compared to that. Now, in the last year, we have a new telescope. It's called the James Webb Telescope, and this is a picture of it. Here is, I think it's 12 or 13 of these hexagons, and it's focusing light on a mirror here that goes to a detector. And now you can even see further. So now we look in between these galaxies, and what you start to see is even more stuff. And what you're seeing now is other stars that we haven't seen before, and then a lot of other stuff that's making stars. So these are the hydrogen and helium atoms that are left over after the Big Bang. So we had the Big Bang, and as the Big Bang expanded outward, and it's still expanding, in fact, it's increasing in its expansion. During all this time, you're making stars. We're going to talk about that. And they're making these atoms that Herb just talked about. The atoms are protons with an electron around it, or maybe just protons and electrons flying around together. So this is all debris here that's going to be coming back together. And we can see out now, looking back to 13.8 billion years ago. That's almost the time of our universe as we know it now. It's almost that's as far back as we can see. There's another few 100,000 years that we can't see back to because of there's such dense matter of ions and electrons that we can't see through it. We can't get light through it. It gets absorbed in that area. So we can see back almost to the very beginning of the Big Bang. You've all heard the Big Bang theory and on television, et cetera, et cetera. So these atoms are coming together now, and ions and electrons coming together, and they're making elements. And then you start to make a sun. And then the sun, which is mostly hydrogen and tritium and deuterium, and when it does its thing and makes it light, it will continue to do that for, maybe 10 billion years. We're 4.5 billion years from on our sun. We're about half-life now. Another 40 billion years, we will have disappeared. But we're seeing the creation of matter all around us, and these stars are generating elements, new elements like helium, lithium, carbon, nitrogen, boron, etc. And all the way up to iron, and it sort of stops at iron until you start to get a lot of neutrons around in some other kinds of stars. And as you get these really large stars with a lot of neutrons in them, they will have a new process going on with the neutrons sort of take over. And then you start to make other heavier elements, the heavier elements in the periodic table. And then we're going to talk in a minute, a second or two away from here, we're going to talk about how you get really heavy elements like lead and gold and uranium and other atoms that time. But here we go. We have the periodic table now that is generated of all these elements. We'll talk about these heavier ones later on. But there's 118 on this graph here, on this periodic table. I pulled this off the web just a moment ago. Of course, there's another one now. There's Tennessean, which was made in partly helped by Oak Ridge work. So this is, well, that is TS. There it is. So this is 118 elements that we know about now. Now, to talk about further, to go any further in this story, I needed to sort of define something called light. The light itself has a spectrum of wavelengths over a wide range, from gamma rays all the way to radio waves. And here's the area that we can see. This little sliver here is red to violet, is the part of the electromagnetic spectrum that we can see. And the speed of all of these waves, independent of the wavelength, is equal to the frequency, the number of these oscillations per second, times the wavelength. The wavelength is the length from here to here, any 2 points on this curve, from there to there, from there to there, and that's what we call the wavelength. And if you multiply the frequency times the wavelength, you always get 299,792,458. That's the speed of light. And it's the same speed for all these wavelengths of light through here, okay? And now if you look at our Milky Way, here we are in the Earth, and we're sort of off on the wing of the Milky Way. The galactic center here is here. And if you look off another direction, you don't see as many stars, but you see a lot of stars in this direction. So you've probably seen that yourself when you look at the night sky. And so what's happened in the last few years, we started to get telescopes that are good enough to see something called a black hole. A black hole is a part of the universe which has so much matter, so many neutrons, that it collapses on itself, and the light itself can't get outside of this hole here. And in fact, the light that you see here around the outside of this is actually light that's going around and around. How does that happen? Well, it turns out that if you put light near a heavy object like the sun, any gravitating body like this, and if you look at the star coming in, the starlight comes in like this, and it gets bent because of the space-time curvature due to the heavy masses right here. So normally, without the sun here, this light would be coming straight in, but now you see it's coming in and bent. And so this black hole is so dense that the light is going around and around in a circle. You remember Newton used to say, if you could stand on a mountain high enough and you throw a baseball fast enough, it'll come around the earth and hit you in the back of the head. Well, that's what happens in the light going around this heavy, dense object right here. And the light can't get out because it'd be easy to show this on a simple equation as to why that's true. And so this is a very important subject right now. And in particular, we can see the evidence for these black holes in outer space. This is the one in the middle of our Milky Way galaxy. We've seen two of them now. We saw one that's 100 times further away than this, but it's a lot smaller than this one. So these objects are out there, and there must be a lot of them. Why? Because we started looking for gravitational waves. Gravitational waves travel with the same speed as light. They're massless. Photons are massless, and they're traveling at the speed of light, and they will get here after a certain period of time, depending upon the distance away. And we have now laser interferometry techniques that can measure the occurrence of these. As the wave goes by, it will stretch one arm of an interferometer relative to the other one, and it will give you a little blip. In fact, they have even concocted the sound of these things as they go by. There's one of these devices down in Louisiana. There's another one out in Washington State. And so when they first turn these things on, and they're really magical devices, they're probably some of the highest quality mirrors and optics and things that you can imagine, and to make this work. In fact, there was a lot of people who didn't think this would ever work, and they had a hard time getting funding for it for a long time. But they've worked. They work very well, and they saw a gravitational wave due to the collision between two of these neutron stars. So they get close enough together that they just merge and give out a big gravity wave. Gravity is quite weak at the distance we're talking about, but if you were up next to it, it would tear your whole body into atoms. But basically, they saw these almost immediately after turning these machines on, and now they've seen many of them, and they've allowed us to do a lot of things. And in fact, when they first started looking at these, they built another one of these interferometers over in Italy, and so they had three of them now, and they could triangulate where it came from, where this gravity wave came from. And when they looked out at this distance where the gravitational waves came from, they saw light that tells them what elements were being generated when these two neutron stars came together. And lo and behold, they saw lots of gold and lead and uranium lines. And so these neutron stars are now coming together. They're massive, they're small, and when they come together, they spew out tons and tons of gold and lead and uranium and other. So we now believe that in the periodic table, these heavy elements here, a lot of them, most of them, are coming from these neutron star mergers. And it just really blows my mind to think that there's so many stars out there and so many of these neutron stars, and every galaxy has one of these in the center of their galaxy. So there are billions of galaxies, there are billions of these neutron stars, and we just hope that one of them doesn't cross our path during our lifetime. That's a very unlikely event, but there's a massive amount of gravitational waves that are kicked out. And well, I'm going to stop at this point and say every student in high school should get a feeling for the grandness the universe expansion is. And I'll sort of stop at that. If there's any questions, well, I'd be glad to try to answer them. This is not what I did during my career, but it's something that occupies a lot of my research and thinking about today. So thank you very much.
Thank you. All right, Fred, you're up. You're muted, sir.
Okay.
Fred, you're still muted, sir.
There's a tradition of causing trouble, and I covered up my Zoom screen with my Word screen. Now, I'm not going to share screen. I'm just going to do a quick introduction, and there I am. So I grew up in Milwaukee, just an ordinary working class family, but I had the opportunity to study nuclear engineering at the University of Madison, University of Wisconsin in Madison. So as I was listening to Herb talk, I thought, that means I'm an engineer with nuclear physics knowledge, but no, I've never designed an atom bomb. I did have an opportunity, it took a little chasing to get it, to have a career at Oak Ridge National Laboratory. And fortunately, once I got into that, I had never had to let go. Now, I'm an engineer as opposed to a scientist. I did a lot of projects at Oak Ridge National Lab. In fact, I originally came in what we called the Central Engineering Group. I wasn't actually lab staff. Eventually, I became lab staff. And I did projects from designing research reactors to waste disposal and decommissioning of old reactors, to medical isotopes, to critical materials, and more. And that's one of the things that I like to tell people about Oak Ridge National Lab. And it's something that I think you probably got an idea of listening to both Herb and Bob, is you don't just do one thing your whole career. You very likely study one thing, but use that knowledge to go into a project that's a little bit different. After a while, you're doing things you never imagined you'd have been doing. I did retire after 40 years, just a few years ago. And now what I do is talk to visitors at the Manhattan Project National Historical Park and the American Museum of Science and Energy. So if anyone wants to come to the museum on Friday afternoons, I should be there. On Saturday afternoons, I should be up at the National Park. Now, when we line this up with Herb leading off, followed by Bob, my job is to bat cleanup. So first question I'm going to have is, does anybody know what batting cleanup means? And when I'm talking, I expect other people to talk. So if we have no baseball fans here, it's when you look around and see if you got people on base and how can you bring them in. And one of the things that I'm going to ask Trixie is what time am I supposed to stop talking?
Well, technically our meeting ends at 8 and we would like to do our incentive prize winner and then close up, but I can give you just a few more minutes if that's
Yeah,
okay.
so I'm not going to spend a lot of time talking then, because the other side of batting cleanup that I had is, what would you rather do? Listen to me talk, listen to questions from the students, which I think would be an excellent thing to do, and then do the wrap up on this. So do any of the students have anything they'd like to say or ask of us?
You can unmute or text in the chat, please.
I saw the question that was directed to me. It was, did you go between Oak Ridge and Geneva? And the answer is yes. I spent, I spent a total of about 10 years for a few months a year in Geneva. And in Oak Ridge, the rest of the year was spent here. But occasionally I went to other labs in between to do other kinds of experiments. We had a lot of traveling experiments. So, so the point is, I did all the development work for what I had to do right here in Oak Ridge, and then I took it somewhere. But it did allow us to get out into the world, see interesting places. That's something that's good for doing science. It's a very international career. It's fun.
I'll step in on that too, Herb. I started out at Oak Ridge High School, and my parents had no money to send me to school. So at the end of my 4 years in Oak Ridge High School, I did quite well in the physics class. And I thought, well, this is pretty interesting stuff. But I had no money to go to college, and I wasn't about. My parents weren't about to pay for it. They weren't going to borrow money. So it turns out, I think a basketball coach. I got to play basketball. I had a basketball scholarship, but it didn't pay much. And so I went to Berea College, where I spent 4 years, wonderful years at Berea College in a small school in Kentucky, where it didn't cost me anything to go. In fact, I made money while I was there, which is kind of amazing. and I played basketball my freshman year, and I was doing pretty well. I was starting, and I was studying, this is pretty exciting stuff. The cheerleaders all hug you at the end of the game, et cetera, et cetera. But then I said, I better get an education. And so I quit playing basketball. I went to the basketball coach and told him I was not going to play basketball anymore. I'm going to get a degree in physics. And I went to my physics teacher, and he said, oh, you can do both. So it sort of told me something. Maybe the basketball coach said you weren't that good, and the physics teacher said it doesn't matter anyway. So anyway, I spent my graduate work out at the lab at Oak Ridge National Laboratory, and then I just stayed on there. I never have interviewed for a job, actually. So when I left the lab, I had 5 job offers around the country, and I took the one at UT, which was also a very good thing, especially since they allowed me to take all my laboratory equipment with me. And so an experimentalist needs equipment, as Herb is telling you. It's very expensive stuff. While I was at the lab allowed me to start a company. So I had a company that was making scientific instruments for almost 25, 30 years. I didn't do much in it except to start it and get the first few years when we built a building. But it was good because people got good job opportunities, et cetera. And then the next thing that I feel very happy about is I had over 50 graduate students get their PhD with me at UT and other places. When I was at the lab, I had people from wherever come to Oak Ridge to work with me for that. And so having all 50 students around the world, and they stay in touch with me. We have Zooms once in a while, but that's also very, very satisfying. Writing these books is also very satisfying. And someone asked about, do I have any simple book recommendations for high school, middle school level students? And the answer to that is no, but I'm thinking about writing one. So stay tuned. I have some more advanced books here, but, and what would be a good place to watch the night's Milky Way with the naked eye? I think you need to find a place where there's not a lot of background light. You might want to check in with the Orion, ORION, Oak Ridge. It's a group that gets together and they have a telescope. It's part of the what's the name of that? It's a junior college in outside of Oak Ridge.
Roan State.
Roan State, yeah, sorry, thank you. And they have a telescope over there, and I think it's every Saturday night.
Well, I think every either first and third Saturday, that might be the physics building at UT.
Yeah, UT has a place there also. But
so I'm gonna chime in, just since I didn't get to do my talk. I'm gonna claim the last minute here. And what's a good place to watch night sky Milky Way? That is a real problem in the eastern United States. There aren't very many good places where you see. I've had some luck going south on the Foothills Parkway past Look Rock. Look Rock is still full of lights from Maryville, but you go on past almost down to 129, and it starts to get a little better over there. Now, next week, we're going to visit our daughter in Montana. And I'm hoping for some good dark sky there, but you know what always happens over there? Clouds. Anytime you want to go, it's either the moon's out, there are clouds, or the rest of the family says, it's dark and cold out there, I don't want to go.
A lot of the astronomers go up to the Big South Fork. That's pretty
well, and that's another thing I was going to point out. Both Big South Fork and Obed, the Manhattan Project National Historical Park works in tandem with those two, at least on a local basis. And both of those have night sky programs. Big South Fork's a little bit distant. Obed at the Lily Bluff crossing is a little bit closer. And get online, look at them, pull up their newsletters, and they'll advertise those in the newsletters. So Trixie, is it time for us to close?
Yes. So if there are any last minute questions, please.
I'll just end. I tend to shoot my mouth off too much, but I'll say one more thing that you probably saw the news today about. We're getting more energy out of the laser fusion problem, and that's a they're talking it up pretty big time. I don't know, maybe not for us, but for our grandchildren or grandchildren's grandchildren, we'll be making our own suns here on the Earth for energy.
Well, thank you so much for all you three for coming by and spending time with us. I'm going to share our screen real quick and then provide the incentive winner for today's meeting. So.
We use a random number generator to give away your prize each week.
And the prize goes to the person who learns how to write and execute that program.
All right, so I was able to pick, and it was Bethany. So thank you, Bethany, yay. Bethany, if you could just email us at prep@utk.edu. Of the 5 prizes, if you could just let us know real quick, what would you like? Can you just unmute yourself so you can say a little quick thing?
The drone?
Drone, it's a popular choice. Okay. So go ahead and then, like I said, email us at prep@utk.edu and then provide your full mailing address so we can ship that off to you. Okay.
Awesome.
And thank you for helping out at the very beginning. That was very helpful.
You're welcome.
All right. So Again, please stay in touch with us. We do have a prep letter, Twitter account, Instagram, and Facebook for Stay Staff. So while you're on break, you can go ahead and peruse that. I do have them pretty updated on a regular basis. And then that concludes our December Virtual Science Club meetings. Again, we're going to be on break for Christmas and New Year's, and we will start up again on January 10th. So there is a QR code there if you'd like to register, but I will be sending out emails, like I said, throughout the break. So if you do miss this, you have links to get in touch with us. And we hope that you have a safe and warm, wherever you're going, trip or staycation here. And we hope to see you next year. All right. Thank you so much, everybody. Have a good night. Safe travel. Bye-bye.
Happy holidays.
Happy holiday.
Au reservoir.
Thank you, guys. Have a good night.
Thank you.